Welcome to the class. In this video, we'll learn about differentiability and derivative of a function, some properties and rule of derivatives, and derivative of a composite function. So let's get started. In our previous class, we have learned the derivative of a function fx is defined as f prime x is equal to limit h tends to 0 fx plus h minus fx divided by h whenever this limit exists and defined. Derivative of function y is equal to fx can also be written as dy by dx or y1 or y prime. At any point x is equal to c, the function will be differentiable when the limit h tends to 0 fc plus h minus fc divided by h exists and finite. That is, at this point, at x equal to c, the left limit and the right limit should be equal. That is, limit h tends to 0 minus, that is the left limit, fc plus h minus fx divided by h, and limit h tends to 0 plus, that is the right limit, fc plus h minus fc divided by h should be equal, and both these values should be finite. Now a function will be said to be differentiable in an interval AB if it is differentiable at every point of AB. Now we will prove theorem number 3, which states if a function f is differentiable at a point C, then it is also continuous at that point. Proof. Since f is differentiable at x equal to c, therefore limit x tends to c fx minus fc divided by x minus c will be its derivative at x equal to c. When x is not equal to c, we can write fx minus fc as fx minus fc divided by x minus c into x minus c. As x minus c is not 0, so this will be defined. Taking limits on both the sides, limit x tends to c fx minus fc is equal to limit x tends to c. As we know that limit is distributive in every situation, so we can write it as two limits. Limit x tends to c fx minus fc divided by x minus c into limit x tends to c x minus c. Similarly, on the left side, we can distribute this limit. Limit x tends to c fx minus. Now fc is constant, so the limit will not have any effect on the value of fc, so it will be equal to fc. Now the first part, this part becomes the definition of the derivative of the function at x equal to c. So this will become f dash c into. Now as x approaches to c, so these two will become closer and closer, and finally they will become equal. When they are equal, x minus c is equal to 0. So the left side will become 0 and the right side is this. Limit x tends to c fx minus fc. This fc will go to the right side. Finally, we'll have limit x tends to c fx is equal to fc. It implies that at x equal to c, its left limit, right limit, and value of the function are equal. It means that fx is continuous at x equal to c. Now, based on this result, we have a corollary one. Every differentiable function is continuous. It means that if a function is continuous at any point, then it must be differentiable at that point. It doesn't mean that if a function is not differentiable at that point, it is not continuous at that point. For example, this modulus function is not differentiable at this point, but it is continuous at that point. Differentiability implies continuity. If a function is differentiable at some point, it must be continuous at that point. But if a function is not differentiable at a point, it may be continuous or it may not be continuous at that point. Differentiable होगा तो continuous होगा ही होगा, but अगर differentiable नहीं है तो continuous हो भी सकता है और नहीं भी हो सकता है. It depends upon the conditions. Now let's consider a function y is equal to sine of cos x square. At any given x is equal to c, we cannot directly find the value of y. First, we have to find the square of x, yeah, square of c. Then at that point, we have to find the cosine value. Then using that cosine value, we'll find the sine of that cosine value. So such functions are called composite function. In our next theorem, we'll learn how to find the derivative of a composite function. Theorem number 4, it is also called chain rule. Theorem 4, chain rule. Let f be a real valued function of two functions u and v, that is f equal to v of u. Suppose t is equal to ux, and if both dt over dx and dv over dt exist, then we have df over dx is equal to dv over dt into dt over dx. If a function is a composite function of more than two functions, we can extend it for more than two also. Now let us solve some problems based on chain rule. The first question is fx is equal to sine x square. We can clearly see that the value of the function does not directly depends upon the value of x. So let us assume t is equal to x square. So now the function fx will become sine t. Where to find the value of d over dx of fx? But this function does not directly depend upon x. This depends upon t. So we'll first differentiate this with respect to t, d over dt of sine t, and t is a function of x. So we'll differentiate t with respect to x. Derivative of sine is cos t into the value of t in terms of x is x square, 2x, as d over dx of x to the power n is equal to n into x to the power n minus 1. This is the formula which we have learned in class 11th. So now substituting the value of t and rearranging, we'll get 2x cos t, and t is x square. So this will be the derivative of fx with respect to x. Now see one more example. Fx is equal to sine of cos x square. Let cos x square equal to s and t is equal to x square. So fx will be equal to sine of s and s is equal to cos of t and t is equal to x square. So df over dx will be equal to d over dx of sine s. Now this is not directly function of x, this is a function of s, so we'll differentiate this with respect to s. D over ds of sine s. Now we'll have ds over dx. Now s is not directly function of x. This s is equal to cos t. So we'll differentiate this with respect to d over dt and s is cos t into dt over dx. Now we can write d over ds of sin s into d over dt of cos t into d over dx of, now t is the function of x, t is equal to x square. Now differentiating will get the derivative of sin s is cos s. The derivative of cos t is with respect to t is minus sin t, and the derivative of x square is 2x. Now substituting the value, s is cos x square, t is x square, and 2x will come as it is. Now rearranging will get minus 2x sin x square into cos x square. This is the answer. Now let us revisit the rule which you have learned in class 11th. Rule number 1. Derivative of u plus minus v is derivative of u plus or minus derivative of v first. Second, the derivative of u into v, it is sometimes called product rule. Derivative of u into v plus u into derivative of v. Rule number 3, derivative of u divided by v is equal to u prime v minus u into v prime. U into v prime divided by v square, and it is called quotient rule when v is not equal to 0. Using these rules, we can easily solve the exercise 5.2. In question 1 to 4, we'll apply chain rule. In question number 5, we'll apply quotient rule and chain rule. In question number 6, we'll apply product rule and chain rule. Same in question number 7 and 8, we'll apply chain rule. Now comes question numbers 9 and 10. In question number 9 and 10, we have to check whether the function is differentiable at given point. Now we'll solve question number 9 of exercise. It says, prove that the function f is given by fx equal to modulus of x minus 1 when x belongs to R at x equal to 1. So we'll check whether the function is differentiable at x equal to 1. How? we'll define the derivative. The derivative of this function f dash x is given by limit h tends to 0 f c plus f dash c c plus h minus f fc divided by h. Now, if this function is differentiable, this limit should exist and finite. So how to check whether this limit exists or not? We'll find the left limit and the right limit. If both are equal, it means that limit exists. How can we know that the limit is finite? Obviously, when this value is finite, it will be finite. So let us find the left hand limit. Limit h tends to 0 minus fc plus h. What is the value of c? C is 1. f1 plus h minus f1 divided by h. H is slightly less than 0. Limit h tends to 0 minus, and the definition is modulus of x minus 1. Modulus of x is 1 plus h minus 1 minus f1, 1 minus 1. This is the definition, divided by h. Now this one will cancel, this one will cancel, this one will get limit h tends to 0 minus modulus of h minus 0 upon h. Now h is slightly less than 0 means it is negative, but we have modulus sign, it's outside, so we will make it positive. Minus of h upon h. Limit h tends to 0 minus 1 is equal to minus 1. So the left limit is minus 1, because this h will cancel this h and we'll get minus 1, and it does not depend upon the value of h. So left limit is minus 1. Left derivative, LHL of f dash is equal to minus 1. Now we'll find R of f dash, right limit. Limit h tends to 0 plus, in this case the value of h will be slightly greater than 0. Definition will remain the same, f x plus h, x is equal to 1 or c is equal to 1. So 1 plus h minus f1. Limit h tends to 0 plus 1 plus h minus 1. We have applied the definition of the function minus 1 minus 1, as fx is equal to modulus of x minus 1, and we know that modulus is always positive, divided by h. Limit h tends to 0 plus, here in this case h is slightly greater than 0, so modulus of h minus 1 minus 1 0 upon h. Limit h tends to 0 plus, as h is positive, so its modulus will be same, h divided by h. Limit h tends to 0 plus 1 is equal to 1. So right limit of the derivative is 1, left limit of derivative is minus 1. So left derivative is not equal to right derivative. It means that the limit h tends to 0, fc plus h minus fc upon h does not exist. It means that f is not differentiable. at x equal to 1. Similarly, in question number 10, we can check the differentiability of the function at x equal to 1 and x equal to 2. What we'll do is, we'll find the left derivative at x equal to 1 and we'll find the right derivative at x equal to 1. If both are equal, then it means that limit exists and it is differentiable. If both are not equal, it means that it is not differentiable. If both are equal but their value is infinite, positive infinity or minus infinity, in that case also the function will be not differentiable. So this much only in this video. In our next video, we'll learn about the derivative of the implicit functions. Thank you.